Okay, so we understand about how we can calculate resultant forces in different situations. Now we move on to Newton laws. In that, Newton first law. What is Newton's first law? Actually, Newton's first law is little modification of Galileo's inertia definition. So Newton's first law states that until and unless an external force acts on a body, it is at rest state or in uniform motion. So this is the same definition given by Galileo also, but little difference. Galileo told that it's a tendency of a body to be in rest or to be in uniform motion. But Newton added that this tendency only possible until and unless an external force acts on the body. So when the external force acts, immediately the body changes its state. It changed its state of rest or it changed its state of uniform motion. For example, take this ball on the ground. It is actually rest state. Now, if we apply force on the ball, immediately the ball rolls. That means the body comes into motion. Because the application of force comes into motion. Suppose a block actually moving. Now you have applied a force on the block. And after some time, the block comes to stop. Means block now into rest state. That means you have changed the motion to rest state. So in these two cases, you are changing from rest to motion, here from motion to rest. And all these changes are possible because of application of force. So until and unless an external force acts on the body is in rest state and the body in uniform motion. But when the external force acts, the body will change their states. Right. Now, see the relationship between inertia and mass. And what is the surprising thing is what is the relationship between inertia and mass? Yes, there is a relationship. I will tell you. See, suppose there is a big rock and there is a small stone. Now you applied same force on the big rock and small stone. Which will come into motion? Obviously small stone because of lesser mass. Mass is less. Whereas this block doesn't come into motion because mass is large. As this body or the big rock not comes into motion because of big mass. Because of big mass, it is in the same state of rest. That means it is in the inertia state only. Because of larger mass, larger inertia. Lesser mass, lesser inertia. So we can say mass is measurement of inertia. More the mass, more the inertia. Lesser the mass, lesser the inertia. Right. So we understand about what is Newton's first law. Now we have to know about what is Newton's second law. Before going to Newton's second law, I will introduce a different physical quantity in this chapter, and that quantity is momentum. Because we should know what is momentum before knowing what is Newton's second law. Because Newton has got the idea of second law because of this physical quantity. So he started thinking like this. Suppose you take a small stone, this is a small stone, and this is a big stone. Okay, now you have thrown the small stone and you have thrown the big stone, both with the same force. Both with the same force. So the mass is very small, Here the mass is larger mass. Now my question is that which body will move with higher speed? Yes, obviously lesser mass. Lesser mass body moves faster than the big mass. That means here the velocity is large, here the velocity is small. So lesser the mass, more the velocity. More the mass, lesser the velocity. So this strike an idea into Newton's mind that mass is inversely proportional to velocity. More the mass, lesser the velocity. Lesser the mass, more the velocity. So then what he's done, he has taken v to the left hand side, m into v, and he changed the proportionality with the equal to with a constant p, and this p is called momentum. So momentum defined as product means multiplication, product of mass and velocity. So momentum P equals to m into v. This is the important formula. And momentum is a vector quantity. It has both magnitude and direction. Now if you take the units of momentum, CGS and SI. So mass into velocity, mass CGS unit is gram, velocity CGS unit is centimeter per second. So gram centimeter per second. Now SI unit, mass is kg and velocity is meter per second. The unit is kg meters per second. Now take an example numerical. There is a car whose mass is 1000 kg, moving with the velocity of 0.2 meters per second. Then find its momentum. Yes, now how do you find? See the formula, P equal to m into v. So momentum P equal to mv, mass is 1000 into velocity is 0.2 meters per second. So it is nothing but 1 decimal 0 is cancelled. So 200 kg meter per second. This is the answer. I'll take the second example. There is a ball of mass 2 kg moving with momentum 15 kg meters per second. Then calculate its velocity. As you know, the formula P equals to m into v implies I am asked to find velocity. So velocity v equal to, take m this side, momentum by mass. So momentum is 15 kg meters per second, mass is 2 kg. So it's nothing but 7.5 meters per second. So this is what the velocity. Right. So we understand about momentum. Now based on momentum, Isaac Newton has derived the second law. He stated the second law. What is Newton's second law? He states that an external force means unbalanced force. An external force acts on a body is directly proportional to rate of change of momentum. This is the statement of Newton's second law. Right. External force acting the body. So F is the external force. Directly proportional. So directly proportional symbol. Rate of change of momentum. Remember, rate means always it is with respect to time. So it will becomes in the denominator. Delta t. Divided by delta t means rate. Change of momentum means delta p. delta is triangle symbol, it represents change. So force, external force is directly proportional to rate of change of momentum. Then to remove the proportionality, we use a constant k into delta p by delta t. Later, Isaac Newton proved that the k value equals to 1 implies F equals to delta p by delta t. So this is Newton's second law. So far, we stated Newton's second law and we have shown the formula F equal to delta p by delta t. Now, based on that formula, Newton has derived another formula called F equal to ma, which is very famous and frequently we use when we are doing the calculations in this chapter. So let me derive F equal to ma formula. So Newton's second law, we know that F equal to delta p by delta t, and you also know that momentum P equal to m into v. P equal to m into v. Therefore, F equals to delta. Instead of P, substitute the P formula mv by delta t. Now F equals to delta means I told change. So change in mass, change in velocity. Generally, when you apply force on any body, body mass generally doesn't change. Only its velocity change. So mass taken to the left, take it from the bracket outside, m delta v by delta t equal to m, F equal to m. Now see this fraction delta v by delta t. Are you remembering anything? Delta v means v2 minus v1, change in velocity. Delta t means time. So change in velocity by time is what? Yes, it is acceleration. So acceleration A equal to delta v by delta t. We learned in the previous chapter. So F equals to ma. So this is the formula derivation from Newton's second law. Now here, if you see the units for force, CGS and SI unit. Okay, first of all, CGS unit, mass gram, acceleration centimeter per second square. Gram centimeters per second square is also called dyne, dyne. This is another unit for force in CGS system. Now coming to SI, mass is kilogram, acceleration is meter per second square, but this kilogram meter per second square is also called Newton. Already we using this unit, Newton. So generally force unit means in CGS we say dynes, in SI we say Newton. So there is a relationship between dyne and Newton, and it is 1 Newton equals to 10 to the power of 5 dynes. So far we learned different forces. If you recall and if you watch the video once again, replay the video and watch it. We discussed about weight, gravitational force. We discussed about friction, contact force. We discussed about normal force, another contact force. So we discussed 3 types of forces: weight, friction, normal. Now I am introducing another type of force called tension. What is tension? This is not the tension like you get tension when the examinations are happening. This is the tension. This is the one type of force acting on a certain type of objects, and those are, tension always acts on ropes and strings. Ropes and strings. Let me explain you. It is a wall. It's a fixed wall, and there is a rope fixed to the wall. It's a rope. From this side, I am pulling the wall. Towards left side, I am pulling the rope, as the rope is fixed to the wall. Now what happens? When I apply the force, the rope has to detach from the wall and it has to come towards me. But initially it won't come. And you feel that some another force is also acting opposite to your force. And that force because of the rope, and that force is tension. So tension is the force always acts opposite to applied force. Remember the definition. It is the force in strings and ropes acts opposite to applied force. That is tension. So if you increase F, T also increases. Say if you increase F from 1 Newton to 2 Newton, T also increases from 1 Newton to 2 Newton. If you increase the force from 2 Newton to 3 Newton, tension also increases from 2 Newton to 3 Newton. Still increasing the force, at one point of time, if you see that the rope breaks, that means your F is become more than T. In this situation only, the rope breaks. Now we see some more examples and applications of this tension. See, there is a pulley. It is called pulley, frictionless pulley. There is no friction. And there is a rope over the pulley. And this one side of the rope attached to a block of mass capital M. And from another side, there is a person standing and he is pulling the rope. He is pulling the rope. So when he is pulling the rope, you know that he is applying the force in downward direction. Then the question is that how much amount of force F he has to apply to lift the block M towards up. To know this, again, this is a rope. This rope also having tension. As the force is acting downward, tension is acting upward. So if you see only this part, in this part, force is acting downward, tension is acting upward. And if you see this part, then this due to block mass M, there is a weight acting downward, and that weight is M into G. And as this weight acting downward, tension always acting upward. So because of this part, tension T equal to F. And because of this part, tension T equal to mg. So if you combine these two relationship, you understand that F equal to mg. That means you have to apply the force which is equal to the weight of the block. Say mass equal to 2 kg. Then the amount of force you have to apply is 2 into 10, 20 Newton. So the minimum force required to pull this block is 20 Newton. More than 20 Newton also you can apply, but minimum 20 Newton you have to apply because F equal to mg. Now see another example for tension. This is a little complicated. Listen carefully. This is called Atwood machine. What is Atwood machine? Here again I am taking pulley. Over the pulley there is a rope and there is two blocks. There are two blocks. Two blocks. Say this block is M1. This block is M2. And here M1 greater than M2. Because of that, when the M1 is going down, M2 is moving up. And this is always frictionless pulley. We are not considering the friction. It's a frictionless pulley. Right. Now here we have to find what is tension. What is tension in the rope? First one. The second one, what is acceleration of the block? So these two things we have to find using Atwood machine, and this is very useful for your competitive examinations too. So let me find these two values, tension and acceleration. Okay, before finding this tension and acceleration, when you take this type of Atwood machine, it's a system because I have two bodies. You divide into two parts and draw free body diagrams. Then it becomes very easy to find out the formulas for tension and acceleration. Let me try. See this one. Consider this rope connected to mass m1. So therefore, what we'll do, I will take this part only. Rope connected to mass m1. Mass m1. Right? This part only I have drawn here. Mass m1. Now if you see, because of body, there is a weight acting downward, that is m1g. As the weight is acting downward, there is opposite force acting in the rope, and in the rope means tension. So there are two forces, tension and m1g acting in this system. But if you see the system, actually m1 is moving downward or upward. Obviously m1 is greater than m2, m1 is moving downward. When the m1 is moving downward, it is having acceleration downward. So when it is having acceleration downward, then the Newton's second law says it has a force F equal to m1a because of acceleration in the mass m1. But this force, this block do not get directly. It got because of resultant of these two forces, tension m1g. Now tell me, which force is greater? Tension is greater, m1g greater. That you decide based on which direction it is moving. As it is moving downward, downward force is greater than upward force. So therefore the resultant force is m1g minus t. And this resultant force is nothing but equal to Newton's force, m1a. Therefore m1a equal to m1g minus t. This is equation 1. So this part is over. Now take this part. If you see this part is moving up. So therefore it has acceleration upward. Now take this part. So I am taking this part here. This mass m2, acceleration is upward. As usual, it is also having mass m2 and g acting downward, weight. And as the weight is acting downward, tension is upward, T. So according to Newton's second law, force F equal to m2a. But this m2a is developed because of resultant of these two forces. And here which force is greater? Obviously acceleration is upward, tension is greater than m2g. So therefore this is T minus m2g. And this is equation 2. So we got two equations, this one and this one. And by solving this equation 1 and 2, you can find tension and acceleration. So let us resolve. So what we do? From this, T equal to, take due to this side, m1a to other side. So T equal to m1g minus m1a from this equation 1. From equation 2, T equal to, take this side, m2g plus m2a. Okay, so then equate them. M1g minus m1a equals to m2g plus m2a. Then take m1a to the other side, it will become plus m1a. Plus m1a plus m2a is nothing but m1 plus m2 into a. This m2g take to the left hand side, it will become minus m2g. Therefore m1 minus m2 into g implies I want acceleration. So m1 minus m2 into g by, take this to left hand side, it become m1 plus m2, which is equals to a. So this is the acceleration of the body. So we have found acceleration a. Now we have to find tension T. So what we do, you have to substitute this acceleration a either in equation 2 or in equation 1 to find T. So I will take equation 1. So equation 1 implies, see, T equals to, this is the formula I found, m1g minus m1a. Now what we do, m1g minus a, na? If you take common, m1 into g minus, instead of a, use this formula, supply this formula here. So m1 minus m2 into g by m1 plus m2. So what happens here? If you do the LCM part, this m1 plus m2 into g minus m1 minus m2 into g whole by m1 plus m2. So I'm writing the next step here, the last step. So m1g minus m1g will be cancelled. m2g plus m2g become 2 m2g, here m1 is there, by m1 plus m2. So implies T equal to 2 m1 m2g by m1 plus m2. This is the tension in the Atwood machine. Now we discuss about Newton's third law. So far we discussed about Newton's first law. So far we discussed about Newton's first law, Newton's second law. Now the last law of Newton's laws, Newton's third law. It is a very simple law and we see so many daily applications in our life. This law states, for every action there is an equal and opposite reaction. Suppose there is a table and on the table there is a book is placed. Now because of the book or because of the weight of the book, this weight applied on the book in the downward direction, let us say the weight is F1. At the same time, table will also apply a force on the book in upward direction, which is F2. Because this F1, F2 forces are equal and opposite, the book maintains the same state on the table and the state is rest state. If F1 is more than F2, the book has to break the table and go inside the table or fall on the floor. If F2 is greater than F1, then immediately as soon as you place the book on the table, the book has to fly away. But both the cases are not happening because how much of force is applying in the downward direction, the same amount of force is applied by the table on the book. So this F1 and F2 both are equal and opposite. And this F1 is called action and F2 is called reaction. So F1, F2 are called action reaction forces. One point you have to remember that this action and reaction forces will act on two body system, not on single body system. That is, Newton's third law is applicable for two bodies, not on single body. I will explain how. In previous class we discussed that there is a body of mass m and two forces are acting, F1 and F2, and told that here F1 equals to minus F2. And here also I am saying F1 equals to minus F2. That means both are, formula wise both are same, but conceptual wise both are different. Here F1, F2 are called balancing forces and F1, F2 are acting on single body. Here F1, F2 are called action reaction forces and acting on two bodies. That's why don't confuse. Newton's third law is applicable for two body system. Now let us discuss some examples where you can apply Newton's third law. example 1. You know this, there is a gun, it's a trigger, and when the trigger is fired, when the trigger is pressed, a bullet is fired and bullet move in the forward direction. And what you experience that this gun will move in the backward direction. So firing of bullet moving in forward direction is action, and because of action the trigger just moves backward, and moving backward is called recoiliness, and that is reaction. So this action reaction pair, Newton's third law example. Now another example, movement of a rocket, or you can say motion of a rocket. General rocket moves in the upward direction against the gravity because of gas burning in the combustion chamber, and this gas comes as gas jet in the downward direction. So coming of gas jet in downward direction is action. Because of that, it applies pressure on the rocket in upward direction, and rocket moves in the upward, which is reaction. Now take another example. This is the water, and this is the, you can say, it's a land. Now there is a boat on the water, and you're standing on the boat, and you want to jump from the boat to the land. So what will you do? When you want to jump from the boat, you just push the boat in the backward direction by kicking the boat with your legs, so that the boat moves in backward direction, which is action. And because of that, you move in the forward direction, or you jump in the forward direction to the land, which is reaction. So like that, we can give so many examples for Newton's third law, because it's a very, very general law where you can apply in your daily life. Okay, now we discuss about the very basic law in physics, and that is conservation of momentum. Conservation of momentum. What is conservation? Conservation is the word used many times in science areas. Conservation means remains constant, or making constant, or never change. So conservation of momentum means momentum remains constant, means P equal to constant. But how? The conservation of momentum principle says that when no external force acts on the body, then its momentum remains constant. This is the statement of conservation of momentum. When no external force acts on the body, then its momentum remains constant. Let us try how it is. External force, so F. According to Newton's second law, F equal to delta P by delta T. And I said no external force means F equal to 0. Then delta P by delta T is also 0. Implies delta P is also equal to 0, because delta T goes there, 0 into delta T is 0. Now delta P is called change in momentum. Change in momentum means final momentum minus initial momentum. Pf is final momentum, Pi is initial momentum, equal to 0. Implies Pf equal to Pi. So what it says, final momentum equal to initial momentum. That means how much starting momentum you have the same momentum at the final also. That is, momentum never changes, but that is momentum remains constant. So momentum always constant when F equal to 0. That is what conservation of momentum. So in nature, you have many activities you are seeing, and all these activities following this conservation of momentum. And this conservation of momentum also is the basis for Newton's third law. Okay, so we understand what is conservation of momentum. Now let us apply conservation of momentum in collisions. What is meant by collision? Collision is nothing but two bodies are hitting with each other, like a car hitting another car, or a bike hitting a wall, a cycle hitting with another cycle. So this hitting of two bodies is called collision. So in this collision also we can apply conservation of momentum. How? See here. Take two marbles having masses m1, m2, and these two marbles are moving in the same direction with initial velocities u1, u2. u1 is the initial velocity of m1, u2 is the initial velocity of m2. Now both are collided. Here collision happened. When collision happens, what happened? This m1 mass applies force on m2. Let the force is F12. Means force by m1 mass on m2. Similarly, m2 also applies force on m1, which is F21. Force by m2 mass on m1. And both are equal and opposite. So this is Newton's third law applicable here. So after collision, both the bodies again are moving in the same directions with final velocities v1 and v2. So this is our case. Now how will you apply conservation of momentum here? Let us see. So at the moment when they are collided with each other, Newton's third law is applicable. So F12 equals to minus F21, equal and opposite forces. Now according to Newton's second law, force is nothing but delta P by delta T, isn't it? It is also delta P by delta T. So delta P by delta T 1 2, delta P by delta T 2 1, minus. Okay, by delta T, keep it like this. Now delta P means change in momentum. Change in momentum means Pf minus Pi, final momentum minus initial momentum. Now see, force by m1 mass on m2. So this force applied by m1 mass on m2. Because the force applied by m1 on m2 changes its velocity from u2 to v2. So I will write like this: m2 v2 minus m2 u2. Now see carefully. I told delta P is change in momentum. Pf minus Pi. Final momentum minus initial momentum. Means final momentum of mass m2, initial momentum of mass m2, equals to minus of, you can keep delta T down. Now delta P, F21, force by m2 on m1. Then m1 changes its initial velocity u1 to final velocity v1. So therefore m1 v1 minus m1 u1. Alright, now you see delta T is cancelled. Let us simplify. m2 v2 minus m2 u2 equals to minus m1 v1 plus m1 u1, minus plus. Now take minus m1 v1 to the left hand side. So then m2 v2 plus m1 v1 equal to this minus m2 u2, take it to the right hand side. So m2 u2 plus m1 u1. So implies, what we understand, that m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. So what this formula says: m1 u1, mass into velocity of the first body, m2 u2, mass into velocity of the second body, and u1 u2 are the velocities before collisions. So this is the plus sign. Plus sign means total. So total momentum before collision equals to m1 v1, mass into velocity after collision of first body, m2 v2, mass into velocity after collision of the second body. That means total momentum after collision. I can say total momentum before collision equals to total momentum after collision. So mathematically it is proved that total momentum before collision equals to total momentum after collision. That means what happened to momentum here? Its momentum remains constant. That is the law of conservation of momentum.